So I included that, jaw, upper and lower, and sites and gaps. I'll explain what sites and gaps means when I introduce the spatial structure. The mean age is 55 years, ranging from 26 to 87. 73% are females. Now this is a very interesting population. Mostly men don't do any work. Females are the one who leads the family. Men are very lazy. So and many of them, they are highly underserved. So many of them didn't have ever had a dental exam all their life. So when the advertisement was done, like when they put out all these flyers that you will get a free dental exam, the females were the one who were coming and doing that. So that is why you end up in 73% females, and we can't do anything about it. The imbalance of male and female in this population, we have to deal with that. 70% have BMI more than 30, so highly obese population. 65% has HbA1c greater or equal to 7, which indicates a high glycemic level. 36% are smokers. So our data is multivariate, that is within site association. In the hierarchy you can think about, and that it can be spatially referenced. It can be spatially referenced across location. That is, it is believed that if one particular site is diseased, it has the potential to influence the disease or periodontal status to a group of neighboring sites. Now, I would introduce what neighbors mean in just a few slides. And it is a mix of continuous and discrete response. So you are interested in joint inference, considering all the response together, considering spatial association, considering the multivariate or clustered structure of this data. But there are some interesting features here. Many subjects have missing teeth, and it is likely that the number and location of the missing teeth informs the subject's periodontal health. So this is where the research gets very exciting here, because we believe that subjects with poor oral health are likely to have fewer teeth than the subjects with better oral health. Tooth location can be informative. That is, if a tooth is absent and located at the back of the mouth, it is usually surrounded by more like poor, it is indicative of the poor health in that region. So they come in clusters. And absent or removed teeth does not at all contribute to the data, and they are not at risk of periodontal disease. So it is more like a monotone missingness type of framework. But not exactly, you cannot think it you cannot really consider it to be like a missing data. I would prefer the term presence absence in this case to be more closer than a real missing framework. So this I would like to consider all these features in my model. Try to start with some exploratory plots, like how are the number of missing teeth behaving when you try to plot them versus mean CAL. So here in this figure, each dot represents one particular subject, where you take the mean clinical attachment loss for all the 168 sites. Now how do you get 168? 28 teeth, and each tooth contributing 6 sites. So you have 168. You take the mean of that. This is very just like a exploratory thing. Take the mean for that, and then you plot the number of missing teeth that subject has. If you fit a simple straight line, you get a highly significant p-value, and that's a regression equation. So, and then we move on. Try to see, just pick one of the most important covariate, age, because I checked with the dentist and they feel that age is very cumulative, that as age progresses, the periodontal health really decreases, like it gets worse. So I chose age and try to plot that. Here, x-axis represent age, y-axis represent number of missing teeth. I did a plot, and it was highly significant, and you can see how the line goes. This is with when you plot age with mean CAL. Once again, significant p-value. What are the existing methods you can do to analyze this type of data? I mean, you can fit a linear mixed model. You can fit generalized linear mixed model. You can fit that separately. You can fit that together. You can fit GEE just using estimating equations. Within cluster resampling was introduced to fit this type of models in Hoffman, which is pretty computationally intensive. But then later on, CWGE, that is called the clustered weighted GE, was introduced in 2003. What they did is that they took the generalized estimating equation, and then they just weigh it with the inverse of cluster size. assuming that the variance covariance matrix is independent. So if you assume independence, which is not a smart assumption, then they showed, I think it's a Williamson and his authors in biometrics, they show that you can do that and get some tighter confidence intervals if you by weighting the estimating equation with inverse of the cluster size. So they did just 1 by ni, or you can throw in as a cluster size as a covariate and then try to model this phenomenon. Some Bayesian treatment is provided by Reich and his colleagues, but none of them really considered spatial association, considered all these 3 types of responses, and then the non-random presence absence of data in a unified framework for periodontal disease. So this is where I started thinking about how to model this all the phenomenon together in a unified model. Now, moment-based CWG considers cluster size, number of present teeth, by doing the weighing of the GE, but they do not consider tooth location. That means I can give you that out of the 28 teeth, you may have 10 teeth, but you don't know where those 10 teeth are missing. Are they missing in the molars or the incisors, or what is the location? So those things were missing. In our hypothesis, we assume that the responses within location are multivariate. Across locations, they are spatially associated, and they probably have informative non-random presence absence, which we assume that these are all caused by a common spatial factor. And additionally, we want to see that if the pocket depth is increasing, so is the clinical attachment loss, and so is the BOP. Now, BOP is a binary, so I mean you should be getting something like a estimated value of zeros and ones when you try to do that. And neighbors should have similar periostatus. So we believe that all these features are due to some common spatial factor, and that dictates all these responses and then the informative presence absence nature of this particular data set. So we want to exploit a unified common structure that accommodates all these phenomena together. Any questions in here? Sure.
The proposition that PPD increases, so does Cal. Cal is PPD minus something else.
Yes,
so
PPD minus.
Functional.
It is automatically it is computed, and you can see from the definition that it is automatically correlated. I mean, so and then BOP is a binary index. So this is where we start to try to think of the model to fit. Like I want to combine all the responses, then the spatial structure and dictating the value of what you get as the response value and all these things in a unified framework. We have 2 continuous. Yep.
I just wanted to go back to your previous slide.
Mm-hmm.
What did you? Yes, that one. Common spatial structure. Would that be sort of like saying some teeth are more prone to disease than others?
Yes, basically what I'm trying to do is that I want to build up a spatial structure inside the mouth, and then that will have some prior distribution, having some mean and variance, and then in that mean component, all the regressors are there. So, in a few slides.
Wait.
Right, I'll show you. So here we have 2 continuous measures: pocket depth and attachment loss, and 1 binary, each for 168 sites out for all the 199 subjects. So YIJS denotes our response. I is the subject, J is the type of response, and S is the spatial location. So I goes from 1 to 199, J is 1 to 3, and S is 1 to 168. Now if the jth response is binary, let's Yij star be the response, and we can use the probit trick to get into a continuous framework. The covariate space is Xi. This is the complete data spatial factor model. So you model Yijs as Aj plus Bj mu is plus epsilon ijs. So mu I is the latent spatial effect that measures the health status at site S for subject I. Aj and Bj are the factor loadings in this factor model. So Aj are the latent factors for the response type J, and epsilon ij is given a normal 0 sigma ij square error. If you compute the correlation between the two, this is the correlation expression. How is pocket depth associated with attachment loss, and then how is pocket depth with bleeding and probing in the continuous transform, and how is the attachment loss with the bleeding and probing. So you get that expression. Now if Bj and Bl equal to 0, then they are uncorrelated, and if they do not share the same sign, you can assess some positive correlation. So we would like to see that BJ and BL get some positive value, I mean, when we do the posterior inference. We assume a Markov random field. These are pretty common in a conditionally autoregressive structure. That is the conditional distribution of mu is conditioned on mu I s prime, where s is not equal to s prime. That density is nothing but the density of the probability of mu I is given when s prime is just a set of neighbors. So you assume this when you try to build up a spatial structure. So we have to determine what our neighboring set is, and that is deterministic. We define our neighboring set and then proceed with our analysis based on that. Now the latent vector mu I, which is mu I to mu cap s, jointly has a multivariate normal prior with a mean vector xi beta, and the covariance matrix is defined as that tau I square q rho I inverse. This is the structure for the autoregression. So you define the matrix M minus rho ID. M is the diagonal with diagonal elements defined as this, and DSS denotes locations S and S prime and adjacent and otherwise. So this is like an introductory slide in CAR. I mean, if you take a book and if you'll be able to pretty much get through it. And this inverse has to exist. There are some conditions that you have to set so that inverse could be calculated. Rho I is the spatial association that goes between 0 and 1. Now this looks like a correlation, but the correct term would be association, because it should be going between 0 and 1. And I want to tell you here that rho of a decent rho should be around 0.8, 0.9, a little towards a 1, because a rho of 0.2 would not reflect quite a bit of would not reflect any substantial association. So there'd be no excitement if you get an estimate of rho of 0.2 in these kind of models. This